Hello everybody, I'd like to go over some polynomial functions, those that we often encounter in high school, at least high school level, maybe early university level. Um, in particular, I'd like to look at the polynomial functions, the linear, quadratic, and cubic. So first, let's just remind ourselves the polynomial is a polynomial p of x, let's say, is an algebraic expression, let me make that subscript 0, of let's say p subscript 0 plus p subscript 1 x to the power 1 plus p subscript 2 x to the power 2 plus, and then a whole lot of other terms, plus p subscript n x to the power n. So the p naught, p1, and all the other p with subscripts are the coefficients of the polynomial. And if we're dealing with a real polynomial, these coefficients are real numbers. And then x is the variable. And in this case, we're just dealing with polynomials of a single variable and eventually functions of a single variable. So just one variable. And then x has different powers. But in order for it to be a polynomial, the powers of x, or the exponents, let me say the exponents rather, need to be positive integers. Exponents are positive integers. No, this is the symbol for integers, just as a reminder. So this means we do not include, for example, x to the power half, which we normally write as the square root of x. This we will not include, and of course we do not include x to the, let's say, negative 1, which is 1 over x. So the first polynomial function we normally encounter is the straight line graph, or the linear function. So let's be more general and just call it the linear function, or let's say the linear polynomial. Let's call it linear polynomial. But actually, the linear polynomial doesn't. Linear polynomial just means the highest power is 1. So the highest power of x is 1. So when you introduce to it at school, normally in the beginning, I don't know, grade 8 or grade 9, it's normally taught as y is equal to mx plus c, where m is the gradient, also known as the slope, gradient or slope, I'll say, and c is the y-intercept. Now, there's nothing wrong with learning it this way. This is very nice and very intuitive, very geometric. But the thing is, you need to, the danger is sometimes students expect to maybe always see it in the form y is equal to mx plus c. And the thing is, you won't all guarantee to always get it in this form. What if you get an expression of the form ax plus by is equal to 1? Suddenly you see something like this, and then you're wondering, what is this? What's going on? And meanwhile, this is just a linear function. This is just your normal function. If you make y the subject of the formula, yeah, you will get y is equal to, let me do it in steps. By is equal to 1 minus ax, and if we divide through by b, we'll just get y is equal to negative a over b x plus 1 over b. And this is exactly the same thing. It's the same, this is your m, your gradient, and this is your plus c, your y-intercept. So a function is, we'll say a map, let me say it like that. A function f, we'll label it f, a function f is a map, or mapping, let's call it a mapping, is a mapping of, I'll say, elements from their domain. This word domain is quite important, to their range, I suppose. sometimes called, depending on the literature, sometimes called a codomain. So I mean, I don't want to be too rigorous here, but the function f takes elements from a certain set, let's say the domain, and maps them to the range. So it's a machine, you can think of as a machine that takes elements as an input and outputs certain values. But what's very critical for a function is that if the function f of x, for every one value of x, it must output exactly one value of y. And so let's use an example. So if we take our domain, let the domain just be, let's do it like this. It's just all the real numbers. So x is just a real number. And our function f of x is equal to, let's say, 2x plus 3. So this is our function. And then on this side we'll have the range, which are our y values, which are going to get output. So let's just pick random values here. Let's say -2, for example. And we're going to throw -2 into our function. And out comes f of -2. And f of -2 is just 2 times -2 plus 3, which is equal to -1. And we can plug in another value. Let's plug in 0, for example. And then it will output f of 0, which is 2 times 0 plus 3, which is just 3. And we can plug in, we said it's the whole real line here, so we can plug in anything. We can plug in a half, I suppose. And this will output f of a half, which is 2 times a half, which is 1, plus 3, which is just equal to 4. So that's what a function does. It takes elements from the domain, does something to it, does some form of transformation, in this case a linear transformation because it's a linear function, and then it outputs the range. Now we often want to plot or at least represent this function graphically, and what we do is we use the Cartesian plane, and I'll use the Cartesian, the xy coordinates. We normally write, I mean not normally, it is this convention to write x first and then y. X is the independent variable and y is the dependent. Now it's important to know that x and y are just dummy variables. X could be time, for example, and y could be velocity. And we could have a scenario where we're looking at how the velocity changes with time. Or we could have something like x being the temperature and y being the length of a metal pole. So we know as we increase the temperature, the length might increase. Higher temperatures cause heat conductors to expand, and alternatively, lowering the temperature could cause it to contract. So x and y are just dummy variables. So before we even plot anything, I just need to mention something here. There's something, whenever we have a polynomial, like the example I mentioned above, the general form, p of x, p0 plus p1x plus p2 x squared plus all the way to p, and there's some terminology that we maybe should cover. So the highest power of the polynomial tells us it's the degree of the polynomial. So in this case, this polynomial is of degree n, because the highest power here is n. A linear polynomial or a linear function, the highest power is 1. So the highest power of x is 1. Now the degree or order of the polynomial. It tells us how many roots there are, or how many solutions there are to the equation p of x is equal to 0. So what happens is, so let me just write that. So the roots of the polynomial are the x values. Of course, x, because we're using x as our variable here, but it could be any variable. The roots of the polynomial are the x values that solve the equation and the equation will be whatever the polynomial is, p of x equal to 0. And if the polynomial is of degree n, then there are n roots. So we want to find the roots of the polynomial. So luckily for us, for a linear function, there's just one solution. So a linear function or linear polynomial only has one root. So only has one root. Now graphically, what this root is, this is where the graph that we eventually will draw, this is where the graph cuts the x-axis. So we could plot this brute force and just calculate x and just pick a few values, -2, -1, 0, 1, and 2, and we can calculate f of x. And we can just, so we can always do this. This option is always available, but it takes time. I mean, even drawing the table takes time. So now what has to happen is now we have to actually calculate this thing. So we already did some of them earlier. I think this was -1. And then if we put a -1 in there, 2 times -1 is -2 plus 3. This is +1. 0 here, this is just 3. This would be 5. And this would be 7. And then we can actually plot these points. Let's put some points here. Let's make this 1. The x-axis, let's make that 2. Of course, this is not going to be drawn very accurately, but the main point is there. And then for the y, I'll make 1 here. Maybe just put 2, 3, 4, 5, 6, and 7. This is quite terrible. But the main thing is let's just get the main point across. So let's start plotting our points. So if we look at this table here, from this table, our points that we can plot is -2, -1. So we always write the x first. -1, +1, 0, 3, and 1, and 5, and 2, and 7. And then we just plot it. We can imagine this is some sort of a grid, and we plot. So when x is -2, y is -1. So the point will be there. I had to write it, to draw it over the 2, unfortunately. -1, when x is -1, y is +1, so we draw it over there. When x is 0, y is 3, so that's on the y-axis. And when x is 1, y is 5. And when x is 2, y is 7. And you can see this is a straight line. And the nice thing is we can just extend it. Okay, I obviously missed all those points, but the point is it goes like that. And then from here we can actually just read off the other values. We don't even need to calculate. We can just draw a dotted line, see where it cuts the graph, and reconnect it to y, and then we'll probably find that is 9. Oftentimes you just want to sketch the graph. So how do we sketch the graph? So to sketch the graph, we just need, for the linear function or for the straight line, we just need the x and y intercepts. we need the x and y intercept. So we need the x intercept, because there's only one x intercept, because there's only one root to the polynomial equation. So we need the x-intercept and y-intercept. And let's see how to get it. And this strategy is true for all the other polynomial functions. So to get the x-intercept, set y is equal to 0 and solve for x. So this is the roots basically, and solve for x. So set y equal to 0 and solve for x. To get the y-intercept, this is normally very easy. Just set x equal to 0 and solve for y. You probably don't have to solve for y, the answer will just be there. So let's see this in action. Our function was f of x is equal to 2x plus 3. F of 0, which means we're setting x to 0, is 2 times 0 plus 3, and this is just 3, and this is our y-intercept. Now, to get the x-intercept, we must do, let me just label it just. To get the x-intercept, we must set f of x to 0 and then solve. So this means f of x is 0, this means 2x plus 3 is 0. And let's subtract 3 from both sides, so we end up with 2x is equal to negative 3. And then we divide by 2 on both sides. X is negative 3 over 2. And if you prefer decimals, this is just negative 1.5. We know that it cuts the x-axis at negative 1.5. Just put that point there properly. And we know it cuts the y-axis at 3. And you can just get a ruler and then draw it. And you're done. That's your whole graph. So one of the reasons why we really love the straight line graph or linear functions is that it's quite easy to see the relationship between the independent and dependent variables. So in this case, x and y. And how we see the rate at which they change, or let me say the rate at which y changes with respect to x, is by calculating the gradient. So the gradient, or the slope, is the change in y over the change in x. So it tells us how y is changing relative to x. So what we can do is, you can just, I'll just draw another sketch here quickly. Just in general, a general Cartesian plane here. So there's our y, there's our x. Just draw a straight line. We can pick any two x values at random, just x1 and x2, let's say. And then their corresponding y values will be, let's call it y1 and y2. And what we can see here is that there's a right angle triangle that's been formed here. And this length, the vertical length, is just y2 minus y1, which is the change in y. And this horizontal length or distance is x2 minus x1. Okay, that's not looking very good, which is the change in x. And why this is nice is because we can pick any two x values across this entire line. So this line can go on for very far, and we can just pick, and that tells us the rate at which y is changing with respect to x. And what does this actually mean? I mean, if we get back to our example of f of x is 2x plus 3, what this is telling us before we even plot the graph, we know a few things here. We know that the line cuts the y-axis at 3. Why? Because if x is 0, that's 0, and then we just have f of 0 is 3. So we know our line is going to cut it here. And what else we know is that our gradient is 2. So the gradient is 2. Now what does that tell us? Well, if the gradient is 2, that's telling us that the change in y over the change in x is equal to 2, which means that the change in y is equal to twice the change in x. So that means if we move one step or 1 unit in the x direction, so let's make that 1, we must move 2 units in the y direction. So we must go here to 5, and we'll draw a dot there. And then continuing, if we move 1 unit, another 1 unit in the x direction, we must move 2 units in the y direction. And that's where our next point will be. And similarly, if we move 1 unit backwards in the left, in the negative x direction, we must move 2 units down the y. So please excuse the fact that the scale is not correct. We draw a dot there, and then similarly we move 1 unit to the left, 1 unit in the x direction, in the negative x direction. We must move 2 units down in the negative y direction. And that's where our point will be. And if we draw the line, we'll have same line that we had earlier, drawn just as badly. So y is changing twice as much as x. Of course, if the gradient was negative, then it would be going downwards. So instead we would have had, maybe let me just physically draw it. Let's imagine we had a graph g of x is negative 2 x plus 3. This one would be similarly 3 is still the intercept, but now if we go in the positive x, 1 unit in the positive x will have to correspond to 2 units in the negative y, and then 1 unit in the positive x will be 2 units in the negative y. That will be our next point. And you can just continue this process. And if we were to join the dots with a ruler, obviously in real life I hope, well then again maybe not if it's a sketch, then what happens is you just have a graph going effectively downwards. So if we read from left to right, we're going down. And if you look at those arrows as steps, it's like we're walking down the stairs. Whereas with the other one, f of x being 2x plus 3, it's like we were going upward. And this is why the gradient is sometimes called the slope. But let's move on to the quadratic function. So I'll do that in another video. Thank you.